Alright, so let's have a look at the inner mechanics of word-to-vec and the tweaks that we need to apply in order to make word-to-vec computationally feasible. First of all, here we have the picture of word-to-vec once more, and we see how each one of our word vectors, each one of our words, of the words in our vocabulary, is embedded in, well, actually two matrices, the input to hidden and the hidden to output matrix, which I used to denote with W and W prime. And you also see here on this picture, which I took from the blog of J. Alomar, the structure of these matrices, and we can think of one as the actual embedding matrix that we use to pull out the embedding of the word whenever we need it, and the other matrix here is denoted as the context matrix. And the term context matrix comes from the fact that if you think about the roles a single word can take in the context of word-to-vec or in the scope of vec-to-vec, we have this prediction task to train the neural network, meaning that a word can appear in two roles, either as the target word or as a context word. And then we can think of these two embedding matrices as one representing the word when it is a context word, and the other representing the word when it is a target word. But, well, for now, take home, or just as a reminder, we have these matrices that represent our words. And let's move on here. Considering the exemplary sentence, "This shall not make machines that think like a human." It's just an example from a famous book, but never mind. We have our left and our right context, and let's focus for the time being on the skip-gram model, which is, from the formal perspective, a bit more handy. You'll see that shortly. If we agree on the word not being our central target word, which triggers a context. So the word not triggers the occurrence of the word though and shall and make and machines. That is the philosophy of the skip-gram approach. And if we assume, that's a simplification, but it's plausible, I believe, if we assume that the context words are conditional independence given the target word, more formally, that the probability of observing the bag of words though and shall and make and machine, given that the word not occurred, that they are conditionally independent, then we can basically focus on the product of the conditional probabilities of one word and the target word, of one context word and the target word, and we can obtain the total probability just by the multiplication of these individual level conditional probabilities, so to say. And, well, the key thing is that thanks to this assumption of independence, we can really focus our attention on the probability of observing one context word. It's denoted here as WO, given a central word, WC. In skip-gram, we have the single sentence word, and we denote it by WC. It will trigger a bunch of output words. Their number depends on our context window, but we have seen, provided we assume conditional independence of the context words given the target word, it's fine for us to focus on the individual ones and try to work out one of these probabilities. P, WO, given WC. And, well, you know how neural networks model probabilities? They do so using a softmax. And that is exactly what you see here. In this formula, we are having a ordinary softmax where we multiply, we compute the dot product of two vectors, UO and VC, and these vectors, they represent the embedding of our two words, WO and WC. And I made sure that the indices indicate the roles, and I also use some color coding here so that we are always aware of the fact that the word WC, which is embedded by the vector VC, that is our central target word in skipgram, which triggers the occurrence of some context word. Okay, so then let's get a little more formal. Now that we know this conditional probability and see we can model that using a softmax, what's the structure of our loss function overall? Well, the loss function, well, we can start with the likelihood, aiming to maximize the likelihood of observing the data, of observing certain combination of words. And the joint probability that we need to maximize here would then be the probability of observing a word, WT plus J, in the context of a central target word, WT. And the context window we can denote by M being some metaparameter, and then we look to the left of our central target word WT, 1, 2, all the way up to M steps. This is the minus M that you see here in the probability, right? And we gain we will go the same number of steps to the right of our target word to obtain the overall context in the sentence, let's say. All the words that are occurring in the context of our central target word. So just to make sure, I think it's not so complicated, but in order to really clarify this bit of the equation here, what's this funny indexing with the J? You also note that J is never equal to 0. So basically here we have J equal to 0 if not is our target word. And then here we have J minus 1, J minus 2, and we have J plus 1 and J plus 2. And with a context window of 2 words to the left and 2 words to the right, these are the words do, shall, and make machines that occur in the context of our central word not. And we multiply over the individual probabilities of the context words occurring. And then we do that over the entire data set. So the first product here, t equals to 1 up to n, that is to say, you know, the inner bit, this is what we do for a single central target word, right? That's what we do for not in the example. This is what we want to maximize for our central target word not, but we don't have a single central target word. We basically shift our window all the way through our corpus, and that is the first product here, this TE from 1 all the way to n, where n then would denote the total number of examples that we have in our training data set. And well, we proceed as usual. Instead of maximizing the likelihood, we're minimizing the log likelihood, turning the product into sums, and that's the first step. And if we assume that we use stochastic gradient descent for training our neural network, then you know that, or I hope you remember, in stochastic gradient descent, we update the weights of our neural network after seeing a single data point. We approximate the full gradient of our loss function with regard to the weights using the residual that we obtain, that we collect from a single training example. And so the SGD effect, it means that we can get rid of the first part. And, well, that does not mean that you can train word-to-vec only using SGD. It's just a simplification that we make here to simplify our notation. Okay, so for the SGD case, the loss function has this shape here. We need the log of the probability of seeing a context word given our central target word, which we basically approximate by this functional. We have the dot product of the two embedding vectors u and v minus the log of the sum over our vocabulary of e to the power of e from the dot product u and v. And that's simply because we apply the log. So we just log the way we measure this probability. We take the log of our softmax classifier So if we take the log of our softmax classifier, and here is our softmax classifier, then this is what we get. Right, the log of the ratio is the log of the numerator minus the log of the denominator, and then basically for the numerator you have the log of e of the dot product, and of course the log and the e cancel out. So this is how this all fits together. And once again, that is our loss function. That's how we measure loss. What I was using for simplification again, squared error loss in an earlier example. So here you see what is really going on. That's our loss measure, at least in the case of stochastic gradient descent, where we have one training data point. We feed one word into our neural network. We calculate the output given the current weight matrices, and then we measure loss in this way here. What's about the gradient update? So far we are now ready to calculate the forward path. We are also ready to calculate the loss, but that's the starting point, and now we have to wonder about backpropagation. What about our gradient update? Well, you have our loss function again. Here's once again, that's just copy pasted from above. That's our loss in SGD. We used to call that, or to denote that by J in earlier examples. So think about it as J, and well, you know how it goes on, right? Now we need to do derivatives. We find the derivative of the loss with regard to the parameters of interest. And the parameter of interest here is our embedding vector, because ultimately we want to learn how to embed words. And we see here on the slide the partial derivative of the loss with regard to the embedding vector v of our central target word, of the word not in my example. And if we, well, the derivative of the loss with regard to vc is then the vector u from our context word minus this ratio that you see, where we have in the numerator and the denominator a sum that runs over the entire vocabulary. So the derivative of log of x is 1 minus log of x, sorry, the derivative of log of x is 1 over x, and this is how the denominator can be explained. And then we need the inner derivative. The derivative of e of x is e of x, and then the next derivative that we need is those of the dot product, and that is uj. It's the embedding vector of the context word u, which is the inverse derivative, and therefore it applies as well on the numerator. And if we then play around with this equation, rearrange it a little bit, we can arrive at the formula that you see at the lower part of the slide, where we have the embedding vector of a context word minus the sum that runs over the vocabulary, which is the conditional probability of seeing some word, wj, given our central target word wc, the word not, multiplied by the embedding vector of that word of word j from our vocabulary. And the key take home here really is this sum, j running over the entire vocabulary. Essentially, what that means is that considering a stochastic gradient descent case, so we are updating the weights after seeing a single training example. And what this formula here is telling us is that this single training example, just feeding the network the word not and seeing what happens, this single training example, the single word not will essentially trigger all the weights in our neural network to get updated. At least all the weights in the hidden to output matrix with W prime. Why only that I clarify later. For now, just look at the formula and note that we update all the weights in our neural network for a single training example. That is what goes happening in the scope of skip-gram training. We feed one training example, we update all the weights. And all the weight means, well, many, because remember, the weight matrices that we have are of the dimensionality vocab size times embedding dimension. And that's typically really big. And because we update so many weights, and because the computation of that sum is pretty costly, the training of the skip-gram model really breaks down unless we tweak it. And for SIBO, I was starting with the skip-gram. For SIBO, you know, in a nutshell, things are the same. Remember that in SIBO, we have multiple context words and use these to predict a central target word. So the probabilities of interest change. The probability of interest now is the probability of observing WC, our central target word, given that all the context word WO1, WO2, WO2M, I was denoting it, occurred. Well, I'm sure this picture, that's exactly this bit, right? Looking at the picture is easier. Well, we once again model this probability using a softmax classifier. And then, well, the working out the loss function and the gradient of that loss function. It's a little more complicated. I was skipping over these steps. If you are interested, you find a little more detailed in our textbook. But essentially, the main take home here is that the update equation, the gradient of the loss function, looks pretty much alike. We have the word embedding vector UC, and then we have a sum running over the entire vocabulary. Again, one of these big sums, and we would once again, because of that, have an update of all the weights in our neural network. So the training of SIBO suffers the same problem as skip-gram, being extremely costly. That is what we can learn from this exercise, looking at the loss function and the derivative of the loss that we need for the gradient update, using either SIBO or skip-gram. They both suffer this deficiency, or inefficiency, I should say. And that is exactly the link to the next part, where we learn about the tweaks that scholars have come up with in order to make training word-to-vec on a large corpus actually feasible. For now, it's infeasible. Theoretically, it's a good idea, but you could not run that on a large corpus of text. It would break down. Because of this complexity, computational complexity, of calculating the full softmax. And both these approaches here, negative sampling and hierarchical softmax, are to address this problem. we start with negative sampling, and I want you to first of all get the overall idea. And the overall idea, I believe, is that we change our classification task from a multi-class problem with very high cardinality to a binary classification. What do I mean by high cardinal? Well, the way we set up our neural network in word-to-vec was we have this output layer, which is 1 to v, and every unit in that output layer represents one class, one word in the vocabulary, so it's super big. And this is what we needed because it's exactly the right architecture to solve this artificial prediction task that word-to-vec is focusing on, where you predict a target word occurring given a context, or where you predict context words occurring given a target word. And what you now do in negative sampling is, let's say we change this fake prediction task and instead consider a task where we want to predict whether two words are neighbors. So as opposed to predicting the probability of the word make occurring after us seeing the word not in a sentence, we change the task, we feed the neural network two words, not and make, and ask the neural network to tell us how likely do you think will these two words occur in the context? In the same context, where context again is defined by some window. And that is a binary problem, essentially. Well, that again is a little simplification. My graph looks as if negative sampling entails training a neural network with a single output node, and that is not the case. But for a start, it's useful to think of that. So we solve a binary problem, which is whether two words occur in the same context. Let's look at the training data and how that would look like. Thou shalt not make a machine that thinks like a human. I took that from the Elema blog, so let's stick with that example. We just need some sentence, right? If there is another sentence you like better, no problem. If we start with the word not and take that as our central target word in a skipgram setting, I'm focusing on the skipgram setting, and for the word not, we have context word though and shalt and make and And for another central target word, say make, again we obtain a bunch of central word or input word, we obtain a bunch of other words. And for simplification here, we imagine that we look at pairs of words, which in practice would not be the case. But it's the same approach to generate training data that you have seen before. The point I am trying to make is another one. Ordinary training data generation approaches, that's a big word, or long construction. Well, the way we construct training data in word-to-vec, it would be just looking at the context and seeing what's going on in that context. We have this window in mind, and we shift this window over our text, and we examine what's going on in this window. What context words occur given a target word, a central one, or what is the target word given a bunch of context words, skip, go, theorem. We always focus on this window, and one window contributes a set of training examples. But for these training examples, the question of whether two words occur in the same context is one by definition. And that's what you see here. This target here, that's our class label. And, well, I'm sure you already grasped that if we construct training data in this way, we will not be able to train a good classifier because we only have one class. By the way, we set up this problem. If we only look at words in the same context or that occur in a context window and then ask word-to-vec, are these words near to each other? Do they appear in the same context? to make a binary problem, the answer will be 1 in every case. So that doesn't work. But our very focus at word-to-vec is to look at context windows of words, words that occur in a certain context together. That's a fundamental principle to word-to-vec. Just that this fundamental principle does not allow us to construct a binary classification task. But thank God we can easily remedy that. And now the term negative sampling makes sense, or starts to begin making sense, because it refers to the fact that we add negative examples to our data set. We know that the word "though" is in the context of the word "not" from our sentence. We know that the word "shalt" is in the context of the word "not," and we know that the word "make" is in the context of our input word "not." And so all the three class labels for these data points are 1, but we artificially sample some other words that we have not seen in the context of the input word "not," where the target label is 0. And the whole point here is to create training data where we have not only positive examples, but a nice mix of positive and negative examples. And then we can do classification. Then we can train a neural network to classify whether two words occur in the same context. If we also present our neural network some cases of words that do not occur in the same context. And that's the principle of negative sampling. And if you understood that principle, that's very good. We can get a little more formal here. Slightly more formally, we first of all consider modeling the event of some context word, and again I denoted by WO, to appear in some window near our target word, our central target word WC. That's the binary prediction task. And then we seek the probability of, if that's an event D, then let's say we seek the probability of D being 1, that event occurring, the two words occurring together in the same context, given the two words, given WO and WC. That is the probability we are seeking. And since it's a binary problem, we could solve that problem using a standard, logistic regression model, or using the sigmoid function here. We take the dot product of our two word embeddings, U, O, and VC. We put that through a sigmoid to ensure that it gets scaled to the range 0 and 1. And this gives us a probability estimate of the words occurring together. And with this setup, we can once again write down the joint probability, where we always run over a context window of M, and then maximize the probability of these words occurring together. And we do this, again, we have it for the entire data set. That's the first product, T from 1 to capital T, for all the possible target words in our corpus. And with this approach, we consider only positive examples with the reasons sketched above. So this approach is not going to work. That is to prepare you for some just notation. And now, negative sampling. So let's denote the event of some word K not appearing in the context of our central word WC. Denote that event by NK. And then, the event of the positive event of some actual context word WO appearing in the context of WC, we could denote by A. And then we can consider a bunch of negative examples, K, denoting the corresponding negative events, N1, N2, N3, and K. And if we are once again ready to assume that positive and negative examples are independent, we can rewrite the equation and of the joint probability, where we had only positive examples, knowing that we couldn't train a classifier in that way. We can rewrite that, which is saying, so in fact we're interested in maximizing the probability of observing a context word given a target word for the positive examples, where we approximate this conditional probability wt plus j given wt. We approximate that by the product that we had before, the probability of the positive event times the probability of the negative event for all the negative words. The assumption of independence is used here and justifies this product that we see. And then basically we say, well, the overall probability is the probability of observing the positive event and those of the negative events. So now we have a new measure of the conditional probability. We have a different way to write down, to capture the probability or to approximate the probability, and this gives us a new loss function essentially. Remember, previously, when making the point that training word-to-vec is extremely costly, we were also starting from this conditional probability here, saying, well, in SGD it's one data point only where we do the updating of our weights. We need one data point. That's the probability. We develop the loss function. You know what I'm talking about, right? Why don't I? Could go back. I have it here in the PowerPoint. Do I not? Here we are. That was our measure of the loss, right? Should use red now. That's what I'm saying. We have this conditional probability of observing a actual context word given the central target word, and that's exactly what we have now in the scope of negative sampling, just that we approximate it by saying, well, this conditional probability is the product of the words that actually occur in the same context, being near to each other. That's the first part. And then we add some negative examples, k negative examples, where we say, well, there the event of the words occurring together is 0. The event is not 0. The event of these words for the negative examples occurring together, this event did not occur. And we take k examples, and this is our new loss function. And with this new approximation, we can spill out the logarithmic loss. So that's our probability, which we want to maximize for our sample. We look at the or the log of that to get rid of the product, turning product into sums, right? And well, you can go through this derivation. It's not dramatically complicated. We get rid of the product by the log, and then we rearrange the equations a little bit. We enter our sigmoid classifier. If the first part is the log of the probability that event D occurs, given that the word WT and WT plus J occurred together, then we can model that using our sigmoid classifier. That's this step. And likewise, we can add the sigmoid classifier to model the event of two words that are not in the same context, not occurring together. And that's all pretty straightforward, I believe. And the key point is that the final equation looks much different from what we had before. Before, we had a sum that was running over the entire vocabulary. And now we have this sum where we have only capital K words or embedding vectors. UHK. So this sum is much easier to compute. And the key implication is that if we feed a single word into our neural network and train that neural network using negative sampling, the single central target word that we put in, denoted by W superscript T here, which has some embedding vector V, this single example will only tweak a subset of the weights in the neural network. And you can get that from the sum. That does not run over the entire vocabulary anymore. Only a bunch of negative samples K, where we can decide how big K is, plus the actual context word. And to stress how this gives you a major speed up, you could consider the size of current of several languages. Here is a little table showing us the size of the vocabulary for Korean and Turkish and Swedish and Japanese and other languages. And for English, it depends a little bit on which dictionary you're considering. Webster's has a little bit more than that of the American Heritage Dictionary. Even that is big enough. We have a vocab size of 350K for English. And this 350K is what we used to denote by V. That's our vocab size. So, sticking to that example of English, training word-to-vec, that would entail, say we have 350,000 words in the vocabulary, and let's say our embedding dimension D is equal to 300, which holds true for both of these embedding matrices W and W prime, then we essentially have in one of these matrices this obscenely large number of weights, all of which we update in SGD for each single word. And even with a powerful computer, that's not gonna work out very well. And if, on the other hand, you use negative sampling, and well, in the paper, Mikolov et al., they were suggesting to use settings of K somewhat between 5 and 20, negative example. So even in the worst, it's not really the worst, but even in the extreme case of considering 20 negative examples, we have at most 21 updates of the weights. One for the target word, that embedding vector gets updated, and 20 for the negative words, their embedding vector gets updated as well. So in total, we have 6,200 updates, which is, well, roughly 0.006% compared to doing the full softmax. So this is a major speed up. And please note that these considerations, they apply only to the weight matrix W prime between the hidden and the output layer. And the reason for that is that we use one-hot vectors. That's important to remember. If you picture the backpropagation equations, the chain rules, we've done it many times, you will remember that as far as the weight matrix W is concerned, the derivative of the loss with regard to W, it entails our input data X. Because we multiply X with W, so the derivative of the hidden layer with regard to W basically is X. And if X is a one-hot vector, it's full of zeros with only a single element in that vector being 1. And because of all these zeros, basically none of the weights in the matrix W will get updated, but the weights of the single row that represents our input word. The embedding of our input word. That gets updated if we feed the input word into the neural network. Its embedding will get updated. And in addition, the embeddings of our k from 5 to 20 negative examples will get updated for the same reason. And these negative examples, these words, are also one-hot encoded, right? And they will get updated, but the other weights we do not change using negative sampling, and this is how we obtain this major speed up. And well, the last question remaining maybe is that what negative examples do we pick? Of course, there is no rule, there is no fixed mechanism, it's stochastic. We just sample negative examples out of the words from our vocabulary, and naively you could just have the probability of every word being given by its relative frequency, which we could basically denote as shown here if we have f of wi denoting the number of occurrences of some word wi in our corpus. So for a word like the, this will be a big number. For a rare word like whatever is a word, h last, that was my example, very rare word, very rarely used in the English language. As a person who never laugh. Very rare word. So there, this f of wi would be correspondingly very low. And then if we normalize that with the size of the corpus v, in this way, we could basically sample the negative examples based on that probability distribution. That would work. In the original paper, however, Mikolov et al. Were recommending some adjustments that they came up with by empirical experimentation, what does work well, what works less well. And just in case you read that paper and wonder what's this 3/4 about, well, they were tweaking this probability distribution from which to sample the negative examples a little bit to increase the selection probability for less frequent words and to decrease the selection probability for many words, for frequent words. It's purely based on empirical experimentation. It's pure heuristic. They found in their experiments it works a little better than sampling the negative examples from their probability of occurring in the corpus. But essentially, this is what you do. More frequent words have a higher probability to get sampled as negative examples. Less frequent words, a lower probability. You scale that, you adjust the scaling of these probabilities a little bit, and then you just draw samples from that negative example, from that probability distribution. And that, in essence, is negative sampling and how it works. So we update only word vectors of a small sample of words per target work, per gradient update, and this helps us to avoid calculating the full softmax, which is very costly. That is the idea. Okay, so let us have a look at a second approach to accelerate the training of word-to-vec and making it feasible, essentially. So in negative sampling, we essentially gave up on the softmax behavior and used the good old sigmoid to solve a bunch of binary classification tasks. And this was reduce the number of word vectors that get trained and updated in one iteration of SGD, stochastic gradient descent. Ultimately, the goal was to reduce the amount of computation, of course. And the second option we have to speed up the training is hierarchical softmax, or SH. Sometimes people just speak about SH, and then that means hierarchical softmax. HS takes a different route. The idea is to retain the softmax behavior and get this nice probability distribution over words in the end, yet with a greatly reduced amount of computation in training. And well, before we go to hierarchical softmax, let's try to understand, or let's look at the classical softmax approach as a very simple and shallow type of tree. Hierarchical softmax uses a binary tree. So before introducing that, let's depict softmax as a tree where we have an input word in the root. That's, for example, a central target word on which we train in skipgram. And then let's say all the words in the vocabulary are sort of right on the next level in this very simple tree. Our tree has v leaves, v being the size of the vocabulary, as always. And then we could basically just depict softmax in that way. And depicting it like that just reminds us how we have one root, but these many leaves next to it, or these many words in our vocabulary, all of which we train if we use word-to-vec without modifications anytime we input one word, which is so costly. In hierarchical softmax, we change the way we compute this tree. And more specifically, we basically compute the leaves in our tree, which are the word probabilities given an input word, which is WC in my notation. WC is our input word. All the other words in our vocabulary can appear in its context. And we compute these probabilities using a multi-layered binary tree. So first of all, what is a binary tree? We organize the words in our vocabulary as a binary tree. And a binary tree is just a tree where after every node, we just have two child nodes, the left one and the right one. And we understand every node in this tree as a word. So the nodes in this tree, they represent words, or more specifically, they represent word vectors. WC denotes our input word. We imagine that we are training on an input word and trying to predict a context word that appears next to it. In my example, we have the case that there was some sentence where we have an input word, WC, and I am. Well, strictly speaking, this is two words, but bear with me. That was the nicest picture of this hierarchical softmax I found. Here our context word is I am. Nodes represent words. First question is, if nodes in the tree represent words, then how do we build up the tree? How do we know which words appear where in the tree? Well, in theory, it doesn't matter. Hierarchical softmax could work with any tree. The structure of the tree is not the point. However, that said, what is true in theory is not necessarily the smartest way, or just organizing the tree in a random manner is not the smartest way to do it. We can organize the tree in a smarter way, and the quality of the approximation of the actual softmax, that could also benefit from a smart way of organizing the tree. And what we use is it's called a Huffman tree. What you need to know about the way this Huffman tree is organized is essentially that we have more frequent words in our vocabulary at higher levels of the tree, and less frequent words we put at lower levels of the tree. And there are ways to construct that Huffman tree sort of, well, not really as a byproduct, but you do construct that when you construct your vocabulary. So it's nothing we really have to worry about so much. And then we have the structure of our tree, and all nodes in this tree, as I said, they represent words and they're word vectors. Now remember that in word-to-vec, every word is represented by two vectors, essentially, because we have these matrices connecting the input to the hidden layer and the hidden to the output layer. And all of these matrices are V by D, size of the vocabulary, and the dimension times the dimension of our embedding layer. And in both of these matrices, which I used to denote with, just to remind you, I used to denote them with, well, just see it in the previous slide, right? We have W and W prime. Actually, this needs to be, that's an artifact. That has to be a V here, because I use a V to represent my vocabulary. And you know how each of the rows in these matrices are word vectors. So that's maybe zoo, and that is, I don't know, tutor, whatever. And we have two of these. In ordinary word-to-vec, in hierarchical softmax, we sort of give up on that. We have one word vector for every word, and the other one, W prime, the hidden to output matrix, W prime, we sort of assign this matrix a different role compared to what it was before. Slightly different role for W prime. And when we train using hierarchical softmax, then we again input a word WC, our target word, and we call the dot product of that target word with an element of the hidden to output matrix. Well, one step back. Our input is one hot, and because our input is one hot, x is one hot, and if we then calculate x times w, because x is one hot, we essentially take out of the matrix w from the input layer to the hidden layer one row, and that is our word vector. And equivalently, this is the hidden layer activation. The word vector is also the hidden layer activation, which we called by x times w. And as we said, this is just one row of w that x is sort of indexing with its one hot structure. And then we obtain the word vector of x. And this is what is WC here, the word vector of our input word that we found in the matrix W, connecting the input to the hidden layer. And we now calculate the dot product of this word vector, the word vector of WC that we found in the input to hidden matrix W, big W, with one vector from the hidden to output matrix W prime. And the element of W prime that we are using is, I shouldn't use red because my graph uses red, is this one. So that's actually a word vector from W prime. And we compute the dot product. And we apply the sigmoid to that dot product to obtain a probability. And what this probability means, or how we interpret the result, is whether from the node of our input word, from the node WC in our tree, should we go left or should we go right to get to this word. And this is how this value that you see here, this 57%, how that emerges. It's how we obtain the 75% in the example, and we interpret that value in that we say if the input word is WC, given our corpus and the tree structure, in 75% of all the cases we find a context word to our input word by going left, first taking the left route. That's the interpretation, which obviously also explains the value of 0.43 or 43% that you see on the other hand side. Feeding in our input word WC, what's the likelihood that a context word can be found by going left or right in the tree? That is the type of question we ask, and the way we ask that question is that we multiply the word vector of WC with the word vector I was just highlighting here in orange. We could also use, we could use that one, right? This is just for example. And that gives us a probability. And from there on, we basically repeat this process, because now that we are in this point here, that's just another word, right? And we do know, we are in the training stage, we have seen I am in the context of WC, so we know where we are heading. We know that from here we need to take one more step to the left. We know that we have to go left at this point. So we calculate the dot product of WC with the word, that's another word vector. It's some word vector. The tree structure is generated together with the vocabulary. As I said, we can do it in a somewhat smart way, but it doesn't matter too much. We know in training that we need to go this way. We need to go left in order to eventually hit the vector of our context word that we are looking for. We calculate the dot product between the word vector of WC and the word vector of the node I have just highlighted in purple. And these vectors, we could say this is U2. Previously I was using the symbol U, and let's say that is oops, U1, and then both U1 and U2 just rows of W prime. This is where we find them. Okay? Calculating the dot product, applying the sigmoid, getting a probability, and the probability is what we find on the path. So we have this, at this point we have probability of 28% and 72% that we get as a result of applying the sigmoid to our dot product. And this is how we eventually arrive at our context word. Every step in the tree, every node in the tree is a word vector that we found in the matrix W prime, the hidden to output matrix. We take the element of the input to hidden matrix W, which now is the only matrix representing our word vectors, and calculating dot products with all the nodes that we find on the path from the input word WC to the context word that we observed in our corpus to co-occur with WC. That's the idea. And these probabilities that you see depicted in the tree, again, we interpret these as the probability to find a context word left of where we are and right of where we are on the path, given the input word. So these sort of capture where in the vocabulary drives the structure of the tree, and the probabilities capture where in the vocabulary, where in the tree we typically find context words given an input word. And note that the structure of the tree is fixed, but that these probabilities that we have on the path, they change with every input word. So the picture you see here is true for input word WC, but if we input a different word, then the probabilities will change. That's important. All right. So that's essentially how this works. And remember that I said earlier on that hierarchical softmax sustains the softmax behavior, and that we do get this nice probability distribution over words in the end. Yeah, and indeed, with every step in our tree, we somewhat decompose the probability of the parent node into a probability of going left and a probability of going right. So revisiting once more the probability of 57 in our tree that we find right next to WC, the probability of going left, that probability, at the next step we decompose it further into a 68 probability of going left again, and a 32 probability of going right after we went left beforehand. And because we only decompose the probability further once we go down the path, the total probability still remains equal to 1. And I think this is also clear when you look at the way in which we compute the conditional probability of PIM given our input word WC, because we calculate that as a product of all the probabilities we find on the path. And if you now imagine we do that for all the words in our vocabulary, we carry out these multiplications, well, then adding up all these probabilities will give you the value of 1 in the end, because the total probability is just decomposed with every level that we walk down in our tree. All right, and now finally, the reason, well, almost done, but the reason why this is speeding up the computations, that is quite similar to negative sampling. In particular, we only update a few word vectors or weights in our neural network at a time. Specifically, we update the elements of W prime, the word vectors, or the weights in W prime that corresponds to nodes on the path that we traverse when going from WC to the context word that currently make up our training example, IM and WC. The word vectors of all the words or nodes on the path from input to context word, they get updated, and obviously also the word vector of the actual input word, WC. So these elements in W, they also get updated. But only these get updated. A proper tree for a real vocabulary would be a lot bigger than what we see here in this example, where essentially we have 8 words. Is that right? Well, we have 8 words at the leaf nodes, but then we have the average, and 12 or 13 words or so. You can count that. It's a number of node minus 1. It's a small tree. And for a real corpus, this tree would be a lot bigger. But still, walking down this binary tree, the number of steps that we make and the number of word vectors that we update per iteration will be a lot less compared to doing full softmax. The complexity of softmax, well, basically, it's over V is the vocabulary, and in a hierarchical tree, convince yourself, that is only log 2 of V. So it's a lot quicker to compute. because we update fewer examples, fewer word vectors, as with negative sampling. All right, and you might wonder why does that work? Why is it that this sort of odd type of training does give us good word vectors? Because don't forget, we do get a probability distribution over words in the end, yeah, as with softmax, but we don't care too much about this probability distribution. That distribution captures the accuracy of our neural network in solving this prediction task, predicting what words occur in the context of an input word. But this task is just an artificial task. We are not really interested in the prediction task itself, it's just a helper. What we are interested in word-to-vec is finding good word vectors. That's what word-to-vec is all about. This is what word embedding is all about, right? So what's the incentive of hierarchical softmax to come up with good word vectors? How does that work? And well, one way to look at that, I guess, is to say that if we have two words that share a similar context, like the words hotel and motel, that was an example we used previously. Hotel and motel, they are somewhat similar. And saying they are somewhat similar, or they share certain semantics, is equivalent to saying they will co-occur with similar words. Similar words will co-occur with the word hotel as with the word motel, because these two words, hotel and motel, are used in similar contexts. That was the whole idea of word embeddings. Remember the distributional assumption and all that like. Okay, so in that case, if the words are semantically similar or share some context, then the context words we see co-occurring with hotel and motel in our corpus, they should also be similar. And given that the tree structure is fixed, the path that we need to take from our input word, be it hotel or be it motel, to a context word will typically look similar. The tree is fixed, the context words are similar by assumption, so when we use hotel as the initial word, we will typically take similar paths, or want to take similar paths to our context words than if we input motel to the same context word. Not always, but roughly, because we believe hotel and motel are similar. And how can we achieve that? How can we ensure that we take similar paths in the tree to arrive at the same context words? Well, the only way to achieve that is that we get similar results from calculating the dot products between the word vectors on the path and the word vector of our input, the root WC in the picture. So if the input word vector of the input word for hotel and for motel, if they look similar, then that will raise the chance that by computing all these dot products with other word vectors on the path to the actual context word, we get similar results. And getting similar results means we take a similar path to the tree, because the path we take is the result of applying a sigmoid to the dot product of two word vectors. And this is why hierarchical softmax will in tendency ensure that the word vectors of words that co-occur with the same set of context words will be similar. And that is exactly what we want. We want a certain similarity between the word vectors for hotel and motel, because they share some similar context. Same with the word vectors of king and queen, which share the context of royalty. And that translates to taking similar path in that Huffman tree, in hierarchical softmax. Right, and well, you can make an attempt to write that down a bit more formally. Have a look at that slide here. The notation looks quite wild at first glance. We once again have a tree. We have leaf nodes that represent context words. We have W1, W2, 3, 4, etc. We have the root node representing our input word. And essentially what we are doing is we are calculating dot products, which you see here. And then you have this funny notation where I have a function that outputs the value of +1 if the statement is true and -1 otherwise, where we basically say there's a node on the path denoted as NWOJ+1, so it's a child node of node NWOJ, whether it's the left child or not. Well, this example is from the textbook, and you find a little more explanation there. I hope that the previous discussion get across the idea. You see the dot products here, and that makes sense because we have the word vector v of our input word, and then we traverse a bunch of other words on the path in our tree, which are denoted by u here. These are the words we pass, and then we need to somehow mathematically to take care about this. Do I go left or do I go right? This is what you see here with this funny functional. And you also see the sigmoid, which basically, so all these computations take part in the sigmoid. It's just a dot product. We give it a sign, then we do sigmoid, and there we go. And we do that. That's maybe also interesting. It's a joint probability we are calculating here for j equal to 1 to L of WO minus 1. What's that? That is the number of nodes on the path from the root node to the true context word W, which during training we know. And you see this split out at the lower part of the slide for the pair of WC as input word and WC as input word and W3 as output word or context word. How this basically probability cooks down to multiplying 3 terms, each of which is a sigmoid applied to a dot product. And that is what we've done before, right? So I hope that helps to get the gist of it. This slide is maybe mainly to make the point, yeah, you can write that down mathematically, but it's clearly enough if you understand the mechanics of hierarchical softmax and how it works and how that accelerates training. Updating fewer weights per iteration. That is equivalent to negative sampling. And then there was a follow-up paper from the word-to-vec team around McAuliffe et al., where they introduced some further tweaks to make the embeddings even better. Just to mention them briefly, we have subsampling of frequent words. That turned out to be a good idea if you have very frequent words in the corpus, then many training examples will be associated with these words, either as input or as context words. That's a consequence of these words being frequent. And so they introduced the subsampling of frequent words, which means nothing but that you have some probability with which you drop words. And that probability you see written down here is a function of the relative frequency of that word in the corpus. In word-to-vec training, you typically do not apply, I should have said that, you typically do not apply stop word filtering as a pre-processing operations. You normally don't do that, but then McAuliffe et al. Introduced the subsampling of frequent words, which is somewhat similar, just that you don't use a predefined dictionary in order to identify what is a stop word and then drop it. Rather, you have a stochastic mechanism to get rid of frequent words. And another extension, which makes sense intuitively, I believe, is that of introducing word pairs and phrases, such that terms like big data or artificial intelligence. In vanilla word-to-vec, you would have a word vector for artificial, you would have a word vector for intelligence, and then you could say, okay, I average these word vectors, and that result of the averaging then is to represent artificial intelligence. But that's somewhat inaccurate, given that artificial intelligence is a phrase, is a standing phrase. So essentially, they analyze their corpus to then have a bunch of word pairs and phrases. Phrase means more than just two words, like New York Times, for instance. And they added that as distinct words. They interpret them as these phrases, the New York Times, that's a distinct word, and it's added to the corpus, and then it gets its own embedding. So you have three embeddings for New and York and Times, but in addition, you have one embedding for the New York Times. Or you have one embedding for big and one for data, but you have an additional embedding for big data. And that additional embedding is to represent the specific semantics of the phrase big data. Right? So just another tweak of word-to-vec. And with that, you have seen the two main mechanisms, negative sampling and hierarchical softmax, to accelerate the training. And in this last slide here, we also commented briefly on some other tweaks. And that really gives you an idea about the core things that you need in order to train word-to-vec or make it feasible. All right, and that also concludes this part on the inner mechanics of word-to-vec, and we can move on with some alternative strategies to build word embeddings.